So in this video, we'll talk about the leading coefficient test, which describes the end behavior of functions. And what we mean by end behavior is as x gets really, really big or really, really small, what's happening to the ends of our graph? What direction are they headed off in? So as x moves without bound to the left or right, the graph of the polynomial function eventually rises or falls in the following manner. So the first thing we need to look at is when n is odd, and remember n is our exponent. Okay, so that's our degree of our function. So what's going on here is that we have this section in the middle. Okay, so this section in the middle, depending on what your function actually is, that section, that yellow section, could change. Okay, so it doesn't necessarily need to be exactly like it's drawn there. However, what is happening, and is the same for all functions that have an odd degree, is they either go up to one side and down to the other, or vice versa. Okay, so how does this work? Well, when n is odd, okay, this will be when our a is greater than 0. So this is when your leading coefficient, your leading coefficient is greater than 0. It's going to behave in this manner. So what it's saying is this arrow right here. As x approaches negative infinity, so the smaller our x value gets, the smaller f of x is going to get. So as x approaches negative infinity, f of x is also going to approach negative infinity. And similarly with the opposite end, as x approaches infinity, so the bigger and bigger and bigger x gets, the bigger and bigger and bigger f of x is going to get. So f of x will also approach infinity. So the second case, however, happens when a is less than 0. So my leading coefficient is less than 0. And when this happens, we see a bit of a change in the graph. So when this happens, as x approaches negative infinity, so the smaller x gets, the bigger f of x is actually going to get. So as x approaches negative infinity, f of x is actually going to approach positive infinity. And it's going to have the same effect with as x approaches positive infinity. So as x approaches positive infinity, f of x is actually going to get significantly smaller here. So this is the end behavior. We're just talking about how the graph goes off at infinity. So let's then take a look at what happens when n is even. Okay, so when n is even, and again, we have this middle behavior that can change. Okay, so we're really concerned with the end behavior, which I'm highlighting here in blue. So these are occurring when n is even. So your degree, remember this is your degree, is even. Okay, so when your degree is even and your leading coefficient, so a is greater than 0, this is what happens. Okay, and you've seen this before in your quadratic equations. Okay, so if we ignore the yellow space, we see that our quadratic equations, when a is positive, they open upward. So both ends of our parabola are pointing in the positive direction. So what this means is as x approaches negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, so as x gets bigger and bigger, f of x is still getting bigger and bigger. So f of x is approaching positive infinity. So these kind of follow a pattern, and you can probably already guess what the next example is going to be. So what this happens whenever your leading coefficient, so a, is less than 0, and your degree is even. So this happens again. We've seen this before. This one is a parabola. So here, as x approaches negative infinity, so the farther and farther and farther out that we go to the left on our x-axis, f of x is approaching negative infinity. So f of x is also getting smaller. And then as x approaches positive infinity, f of x is still going farther and farther and farther down toward negative infinity. So we can use that information about the leading coefficient and the end behavior to describe the end behavior of the graph of the function. So all of the things that we've been doing recently help us to be able to graph this function more accurately without the use of some kind of graphing tool. So here we can see that my leading coefficient is 1, okay? And my degree, and this is where we used n, is 4, and 4 is even. So I'm looking at an even function with a leading coefficient that's greater than 0. Okay, so let's describe the end behavior of this. So you're going to go down to where you had your part 2, so when n is even, okay, and your first example where a was greater than 0 because 1 is greater than 0. And then we can describe the end behavior of this function. So this is simply as x approaches negative infinity, f of x is approaching positive infinity. And as x approaches positive infinity, f of x is also approaching positive infinity. Similarly, we can look at example 2 here. So with example 2, we see that our leading coefficient is 1, which is greater than 0. And our degree here, remember that was our n, is odd, okay, because it's 5. So here we need to look at when n is odd and then describe that end behavior. So when n is odd, we know we're going off in different directions at the end behavior. And when our leading coefficient is positive, the direction of our end behavior matches the direction that we're going in x. So if we're heading with x, as it approaches negative infinity, f of x is also approaching negative infinity. And as x approaches positive infinity, f of x is also approaching positive infinity. So we can describe our graph now in this type of manner as well. So let's take a look now at these zeros of polynomials. Zeros tell us a lot of information about polynomials. So for any polynomial function f of degree n, the following statements are true. So the graph of f has at most n minus 1 turning points. Okay, turning points are points which the graph changes from increasing to decreasing or from decreasing to increasing. Additionally, the function f has at most n real zeros. Now, we could have imaginary complex zeros, but what we're talking about here is that the function has at most n real zeros. So if we have, if we look back up above to example 2 there, our degree is 5, so we have at most 5 real zeros, and we have at most 4 turning points.